Hello, Math 2. This is Mrs. Bricky. This video is for Unit 4, Lesson 1. We'll be talking about scale factor and dilation. So, first definition, a transformation that changes the size of a figure but not the shape is called a dilation. So you can see that I have a kind of a kite shape right here. That's my original figure is the one on the left that's kind of small. And if I dilate it, if I change the size of the figure but not the shape, so in this case I made it bigger, that scaled copy is a dilation of the original figure. Sometimes that will be called the image. So if we maybe measure this original kite right here, it had a side length of 4. And if I measure my image or my scaled copy, it has a side length of 8. So scale factor is the factor by which every length in the original figure is multiplied when you make a scaled copy. So if you think about, the original had a length of 4 and the scaled copy had a length of 8, I just doubled the side length, or in other words, I times it by 2. So for this dilation, the scale factor is 2. If you ever have a situation, though, like maybe it was easy for us to see that 4 times 2 gives us 8. But oftentimes the scale factor isn't easy to just eyeball like we did. So if you ever need to calculate the scale factor, you just take the new length on the shape and you divide it by the original length. So that would give us 2 if we took that 8 and divided it by 4. So if you ever have a situation where, the scale factor is not something you can really tell, like if it was a 3.1 and a 12.4, you could always just divide the new length by the original length to get the scale factor. Okay, so in math, we have 2 types of dilations. So if you have a shape like triangle A here, and it becomes larger like triangle B, so if A is dilated to give us B, in math we call that an enlargement. And we're going to go ahead and calculate the scale factor of that enlargement. So if I think about maybe the height of this triangle, the new figure has a height of 12. The original figure A has a height of 4, and 12 divided by 4 is 3. So this is a scale factor of 3. All of the lengths are 3 times as long. Okay, on this next dilation over here, if I started with triangle B and it got dilated to become triangle C, that type of dilation in math is called a reduction. It got smaller. So the scale factor for this, if we think about our new shape, shape C, it has a height of 4, and we want to divide it by the original, and that has a height of 12. So 4 divided by 12 is the same as 1/3. For scale factors, it's probably a good idea to keep it in fraction form. We don't really want to have like a decimal form like this. We'd much rather have fraction form. So for each of these pairs of shapes, we're going to find a side length, either x, y, or z, depending on the shape. And then we're also going to find the scale factor. So our first pair of shapes here, it's a dilation from C to D. So C is our original shape and D is our new shape. So to calculate the scale factor, we're going to take this new length right here, 18, and divide it by the original length, which is 12. And 18 divided by 12 is the same as 3/2. So our scale factor of our dilation is 3/2. So what that means is that I can multiply the 12 by 3 halves to get 18. And it's not just that side gets multiplied by 3 halves, it's that all lengths get multiplied by 3 halves. So if I want to calculate the value of x, I just need to take that 4.2 and multiply it by 3 halves. And so that gives me, if I do that in my calculator, a length of 6.3 for x. Okay, our next dilation is a dilation from E to F. So our original triangle is E, and our dilated copy, our scaled copy, is F. So this is my original, and this is my new. All right, to calculate the scale factor, we need to do new divided by original. So I'm going to use these sides down here because we know that this one is 7 and we know that this one is 14. So if I take the new length and divide it by the original length, that is equivalent to 1/2. So this is a dilation with a scale factor of 1/2. So that means 14 is multiplied by 1/2 to give me 7, and that works for all of the sides. So if this side in E is 16.8 and I want to solve for y, I just need to multiply by 1/2. Well, 16 multiplied by 16.8 multiplied by 1/2 gives me 8.4. Okay, our last one on this slide, we have these two semicircles. Our dilation is from H to G. So my original shape is shape H, and my new shape is shape G. So this is an enlargement. It got larger or bigger. For the scale factor, I want to take the new length, 20, and divide it by the original length, 12. And 20 divided by 12 is the same as the fraction 5/3. So our scale factor for this dilation is 5/3. We want to calculate this arc length right here. So that's called, given the letter Z, the original shape's arc length is 6. So the scale factor tells me that each length in this shape is multiplied by 5/3. So to calculate the length of Z, we need to take the original length and multiply it by that scale factor of 5/3. And when we do that, we find out that Z is, whoops, don't know why I wrote 2. Z is 10 pi. And you can get that, of course, from, just inputting this into your calculator. All right, so we found all of those scale factors and lengths. So scale factors are multipliers. Important to remember that. It's not about how much you're adding, it's about how much you're multiplying. If you had a scale factor of 1, which isn't really a scale factor we use very often, the size of the new shape would be exactly the same. Wouldn't change. If you took a side length of 5 and you multiplied it by 1, you would get a side length of 5. So k equals 1 would give you a shape that is exactly the same size. Well, if you want to make the shape larger, if you want an enlargement, then that scale factor has to be bigger than 1. So that could mean that it's a whole number, like 2 or 4 or 6 or 3. Those all would make the dilated shape larger. But it also just means it could be any number larger than 1. For example, a scale factor of 3 halves or a scale factor of 7/8, because those are both fractions that are larger than 1. So any number larger than 1. If you had a scale factor of 1.01, it would make the shape, it would make the dilated copy slightly larger. Anytime your scale factor is a number less than 1, you're going to have a reduction or a smaller shape that is the result of that dilation. So for this example 2, we have a shape Q, And Q is this little shape right here. And shape Q has been dilated several times. And we have, in fact, 6 scaled copies of Q. Now, don't whip out your ruler because these are not exact. We would like to just match each of these image to the scale factor that most likely created it just by thinking logically about fractions, not about measuring. So I have a bank of scale factors up at the top, starting with k equals 1, k equals 2/3, k equals 5/4, and there are some extra scale factors up here, so we're not going to use them all. And our goal is to match each of these shapes to its appropriate scale factor. So first of all, let's start with k equals 1. Can you spot which shape is exactly the same size? And hopefully as you're looking at those, you can tell that the shape that is exactly the same size is this one. So that would be a scale factor of 1. And I can actually move my little highlighting over there and you can see that it is exactly the same size. Let's start with D1 now. D1, D4, and D5 are all reductions. They are all smaller. Like if I drag this over, you can see that they are all smaller. So for D1, it's smaller, but it's not a lot smaller. If we think about our fractions, and hopefully you kind of just looked at these and maybe decided, we've got several that are smaller than 1. 2/3 is smaller than 1. 1/5 is smaller than 1. 1/10 is smaller than 1, and 1/2 is smaller than 1. So for D1, we're looking for one of these scale factors to be matched up. Well, 1/5 and 1/10 are both very small. So I think we would be choosing between 2/3 and 1/2. Well, if you think about 1/2, half of this, if we multiply it by 1/2 so that it's half as long, it would be about that big. But it looks like D is larger than that. D1 is a little bit bigger than half. So we need a measurement that is a little bit bigger than half. And so that is going to be the 2/3 scale factor. And if I think about this one, this is the one that's about a half. So that would be k equals 1/2. For D4, it looks like we're deciding between 1/5 and 1/10. So we would kind of be thinking about, can we fit 5 of these? Is this 5 times as long, or is it 10 times as long as that little D4? But so hopefully you found 1/5 for that one. So 1/10 looks like it's extra. 1/10 scale factor would just be absolutely tiny. Like just this a very, very, very little shape. Well, I think I just drew it way too tall, but just very, very tiny. About 1/10. Okay, so now let's look at those two shapes that are much larger or larger than Q. So for D2, it looks like it's larger, but it's not a lot larger. Sometimes with fractions that you aren't sure how big the fraction 5/2 is or how big the fraction 5/4 is. So if you're ever looking at a fraction and you're not sure its size, sometimes it's helpful to look at the decimal equivalent. 5/4 is 1.25. 5/2 is 2.5, and we also have a 4 over here. So definitely D2 is not 2.5 times as long as the lengths in Q. Probably not even 2.5 times as long. It's going to be this one, 5/4. And then for D6, we could think about, do we think it's 4 times as long or 2.5 times as long? Well, if I think about that length, I think this would not be 4 times as long. It just looks like about 2.5. So 5/2 for that one. Okay, sometimes instead of labeling a shape, we would label the vertices. So my last few shapes, I just gave them a letter, but now this shape has vertices labeled A, B, C. You probably are familiar with this type of notation from your math class last year. And when we have the dilated shape from that original shape, we often use an apostrophe with the same letter, and we would read that apostrophe as prime. So this is triangle A prime, B prime, C prime. Point A and point A prime are called corresponding points. So every dilation originates from a fixed point. And if you connect each point on an image to its corresponding point, the lines will intersect. So if I connect A to A prime, and if I connect B to B prime and C to C prime, you can see that those are all converging upon that point P. That point P is called the center of dilation, and every dilation originates from a fixed point like that, that's called the center of dilation. So here's two triangles. We've got EFD, EDF, DEF, whichever order you want to call the triangle. We want to draw the projection lines from each point to its corresponding point on the image, and then that will help us find the center of dilation. So sometimes when people do this, they aren't sure which side of the shapes that the center of dilation will be on. If you extend the lines to one side and they don't intersect, just try extending them in the other direction, and they will intersect on one side or the other. So here's point E. We want to draw a point through E prime, and I'm just going to try to make this nice and long so we can find where it intersects. Pretty close, not great. Sorry. Connect F to F prime as best we can, and then connect D to D prime as best we can. And obviously, if you're doing this on paper, it might not be perfect. Like, whoa, what is happening? Why are they not intersecting? I think it's that my first line is not very good. Didn't really go through E prime. There we go. Whoa. So you can see a little bit, if you're a little bit off with one of your lines, it can kind of make a big difference. But if you're really precise in how you draw your lines, you should see all of those lines, those projection lines, intersecting at the center of dilation. If you've taken an art class and done perspective drawing, in art class they call this the vanishing point, and in math we call it the center of dilation. So here we have triangle ABC and its dilation, triangle A prime, B prime, C prime. We want to figure out the center of dilation here, and then we want to decide if it is a reduction or an enlargement. So I'm going to get my little line tool back out and try to find the center of dilation here. So I'm going to connect point C to point C prime. Point B to point B prime, and point A to A prime. So when we connect those corresponding points, we see that the center of dilation is the origin, the point 0, 0, right here. Next question says, is this a reduction or an enlargement? Well, our original shape is the blue shape, ABC. I know that because it's just the regular letters ABC. And the dilated shape is A prime, B prime, C prime, which is larger than the original triangle. So this is an enlargement. And to figure out the scale factor, we need to take a length in the new shape and divide it by a length in the original shape. This is kind of awkward because none of those lines, none of those segments are, where we could count them on the coordinate plane or count their length. But definitely we have math tools we could use to calculate those distances, but you can use any corresponding length of two figures. And so one thing that I think is kind of interesting to use here, which is valid, is we could use the height of each of those triangles. So our new triangle, our red triangle, has a height. Well, its lowest point is at 2, and it's a height of 2, and its highest point is at 14, so that's a height of 12. And our smaller triangle's highest point is at a y value of 7, and its lowest point is at a y value of 1, so that's a height of 6. So it can be any corresponding length, which doesn't necessarily have to be one of the sides of the shape. So if we want to find the scale factor here, it's the new length, which is 12, divided by the original length, which is 6, and so our scale factor is 2. All right, we want to look at these points now just for a second to see if we can notice anything. Point A, it's written down for us, it's 3, 1. And now let's write down the coordinates of A prime. A prime is right here, that's the point, 6, 2. Point B is 5, 7 right here. And point B prime is 10, 14. Way up high. And our last point, point C, is 1, 5. And if we find the location of C prime or the coordinates of C prime, that is 2, 10. So when you're looking at all of these, hopefully you have noticed that not only is that scale factor multiplying the lengths in the shape, it also multiplies the coordinates of the shape. So with a dilation, it's not just about the size of the shape, it is also about its position, and its position is relative to that center of dilation. Uh, so multiplying the coordinate points of these shapes that we want to dilate will actually help us not just find the right size, but also find the correct position of the shape. Now, this only works for dilations that are centered at the origin. So that is one thing to bear in mind, is that our center of dilation has to be the origin for this to work. Let's try using that idea for the video. I'm going to skip this because videos get long. Let's use that idea to try to draw a dilated copy of this trapezoid. So the trapezoid ABCD is graphed for us. We are going to try to graph its dilation with a scale factor of 3. So on our original shape, point A is at -3, 1. Point B is at -1, 4. Point C is at +2, +4. And our last point is at an x value of 3, y value 1, 3, 1. Okay, so since our scale factor is 3, we can multiply those points by 3, and we are multiplying both the x and the y coordinate. So this would be -9, 3. So if I plot that point, this will be the location of A prime. If I multiply the coordinates of point B by 3, I get that B prime is located at -3, 12. That would be right here. And point C, when I multiply by 3, gives me the location of C prime. So that would be 6, 12. And our last point D, if I multiply that by 3, I get point D prime is 9, 3. So if we connect those points, it will give us our dilated shape. A to B prime, B to C, C prime to D prime, D prime to A prime. There it is. So another thing to notice that I think is great to notice is that if you look at the slope of one of the sides in the original figure, the slope of the dilated shape is the same. In other words, they are parallel because their slopes are the same. So that is a great way to check if your dilation is correct. You can just check and see if those sides are parallel to the original. Okay, we can do this for just even something as simple as a line segment. So if I have a line segment ST, S is at -4, 2, and T is at the point 4, 6. We want to dilate it with a scale factor of 3/2. So if we multiply by 3/2, that will give us the location of S prime T prime. So S prime is going to be located at -6, 3. And again, I just did -4 multiplied by 3/2 and 2 multiplied by 3/2. You want to multiply both the x and the y coordinate. So let's plot that, -6, 3, that's S prime. And point T will be, its new location, T prime will be, what do we got, 6 and 9. Here's my location for T prime. And if I connect those, that should give me, because it's a dilation, that should give me a parallel segment, and its length is exactly 3 times as long as the original. And you can see that it definitely is parallel. This has a slope of 1/2, and then this one also has that same slope of 1/2. Okay, we're going to make a dilation with a scale factor of 2/5. We're going to actually, in this case, graph the original and graph the dilated copy. So point J is at 5, 5. Point K is at 10, 15. I guess I should label these. And point L is at -5, 10. So this is our original shape. And we want to make a dilated copy of that with a scale factor of 2/5. So if we multiply 5 by 2/5, we get 2. So J prime is going to be located at 2, 2. 10 and 15, when we multiply those by 2/5, we get 4 and 3. That does not seem right. 6, 4 and 6. Sorry, I miscalculated. 4 and 6. You know how I caught my error? I caught my error because I could see that it was not going to be parallel. So that's a great way to catch an error. There's K prime. And then L prime is going to be -2 and 4. Let's see if I calculated that one right. Let's see, if we graph this little shape, connect those, it should give us some nice parallel segments, and it should give us a perfect little scaled copy with the scale factor of 2/5. So each length in that original is, or each length in that new triangle is 2/5 as long as the original. Okay, dilations can be done from other fixed points. It doesn't have to be from the origin. For the purposes of the video, I'm not going to go into that, but if you are interested in that, the way that you do that is through using vectors. And so if you have interest in the idea of dilating from other points, you can let your teacher know, and I'm sure they would be happy to explain that to you. You won't need to know how to do dilations from other fixed points for your homework assignments. It's just something kind of fun that we did in class. So, all right, that's it for this lesson. Let me or your teacher know if you have any questions. Thank you very much.